So,
Okay.
welcome everybody to this second in the Cyberseminar series that's concerned with the Summer Institute at the National Water Centre. We want to welcome today Dr. David Gochis, who's with the National Centre for Atmospheric Research in Boulder, Colorado, and he's also the developer and lead person for the WRF-Hydro System, which is the framework that's been used by the National Weather Service to create the National Water Model. So we want to welcome you, David, and look forward to your presentation about the National Water Model implementation using WRF-Hydro.
Great. Well, thank you very much, David. Thank you, Emily and Liz, folks from Kawasi. I'm going to talk here in a bit more detail about some of the underlying model configurations which make up the National Water Model. I was not able to join the call last week with Ed Clark on the line, but I did go back and review the YouTube presentation, so I think I got a pretty good idea of where they left off with theirs. So I'm going to try and dovetail in as closely as I can with that talk. That talk was largely focused sort of at the high programmatic level in terms of the vision and the motivation for the National Water Model, as well as some initial looks at what kinds of products are being developed out of the National Water Model. Today we're going to sort of dig into a little more detail into the underlying model setup and model architecture that's been under development really just for the past 2 years as this effort is sort of ramped into high gear. And so you'll see that there is some areas which are clearly a little better developed and areas which are still sort of undergoing some rapid development and improvement. But suffice it to say, it is a large, sort of fast-moving effort. So I'm merely just a presenter here. I definitely want to acknowledge the fact, as noted on this title slide, that there is a very large integrated team of people working on this between the National Water Center, within NOAA, many now of the regional forecast offices, which are heavily involved in model evaluation, our group here at NCAR, and many within the academic community, in the Kawasi community and beyond, that have been looking at various aspects, strengths, weaknesses, new developments within the National Water Modeling System. And so I'm going to try and briefly summarize what has gone into operations and hopefully use that as a platform for some discussions at the end about some new developments that are going on, and if folks have questions on potential interactions and things like that, we can certainly get into that. So broadly speaking, this is the outline for the talk, more for posterity as it goes online. We'll be reviewing the current National Water Model configurations and the model setup, how the forcing data, the meteorological forcing data is prepared, what some of the underlying physics representations are. I'm not going to go into sort of equation level detail with a lot of that, but sort of a conceptual description, and then relate that to some of the current products that are being generated. I'm going to mention briefly also this WRF-Hydro evaluation and verification system, which has now been sort of stood up and released as a community piece of code. We get a lot of inquiries from the community, sort of the broader community of WRF-Hydro modelers and developers about what kinds of evaluation and verification tools and calibration tools exist. And so this WRF-Hydro system is something that's been created that helps support a lot of the ongoing analyses that are being done. I'm not going to talk in too much detail about results to date. We're slowly starting to roll these out in a number of different presentations, both within the Weather Service and beyond, and getting into some publications. But there is a number of different things that have been analyzed to date, and we'll mention a few of those towards the end, and then we'll try and wrap up. So one of the things that is important to keep in mind is what is the goals of the first version of the National Water Model. Ed Clark will have talked about sort of the longer-term vision about why NOAA has embarked on this effort to build a really sort of a seamless National Water Model, as opposed to going about hydrologic forecasting in a different way of what's been traditionally more done, which is sort of a basin-by-basin approach, or a catchment or watershed-by-watershed approach. And where does this new National Water Model fit into a number of the different existing forecast services that already exist? So this slide here really tries to articulate what some of those goals are. One is to provide operational streamflow guidance really for currently underserved locations. These are places across the country which have no hydrologic forecast information, either by the River Forecast Center forecast points or by a number of other federal entities that are providing information on water resources at those points. So this is really getting at trying to provide a more continuous and uniform level of forecast service, or at least forecast guidance for the country. The next bullet speaks to the issue of trying to develop sort of a continuum of hydrologic characterization in terms of analyses and forecasts for a number of different variables, not just stream flow, which is what has traditionally been the main hydrologic forecasting component, but also now getting into doing a number of different kinds of forecasts for things like snowpack, soil moisture, obviously channel flows and major reservoir inflows, but also even more recently, as evidenced by some of the large flooding events we've had this summer in Baton Rouge, in Iowa, and now along the East Coast with Hurricane Matthew, looking at different ways to predict flood inundation. And so some of the data that's coming directly out of the National Water Model, and then also a number of value-added products that have been developed, particularly by David Maidment and his group at UT Texas and folks in Illinois, and sort of a large collaborative group there, looking at taking National Water Model output and translating that into detailed, almost engineering scale flood predictions, inundation predictions. So once that data is sort of stood up and sort of flowing out of the modeling system, the next goal is to begin to interface that data, those kinds of hydrologic products, into this geospatial intelligence framework. And that's a fairly sort of sophisticated way of saying where is the water, where are the risks related to the water, and what are the potential impacts going to be in terms of impacts on people, on transportation, on emergency response services, on certain vulnerabilities. And so when you think about hydrologic information and geospatial information combined on various platforms like a GIS-based system, we now have the capability to provide intelligence in terms of advanced decision support for basically predicting and handling and mitigating these risks. So that geospatial intelligence framework is a new activity within the National Water Center and within NOAA and its partner agencies to really help improve resiliency in a number of ways. The final bullet is really more of a long-term goal that the National Water Model provides just an initial step on, and that's this migration from, or in addition to some of the existing hydrologic forecasting methods, to a more Earth systems physics-based approach to modeling. And Ed Clark spoke a little bit about that last week, about where and why does it make sense to do that kind of approach in addition to the existing forecasting approaches that already exist. Obviously, there's opportunities that get opened up here to sort of rapidly look at and experiment with new modeling techniques, new data, particularly remote sensing data, new sensor networks, and really different ways to try to assimilate that information into a modeling system. So, but that's just groundwork. We obviously haven't done all that in version 1, but these 4 bullets here really spec out the priorities for where version 1 is directed to sort of orient the future model development efforts. Taking from a slide from Ed's presentation last week then, just to describe the underlying architecture of the National Water Model is this community WRF-Hydro System. It's been developed by a number of different collaborative groups, both here in the U.S. and around the world. For the last 10 years or so, it's undergone a couple of different iterations. This is actually our 3rd implementation as a national forecasting system with WRF-Hydro, and each one has a number of different configurations and data sets and things like that have gone into it. But sort of the underlying attributes of the WRF-Hydro system itself are that it is configurable in a number of different ways to deal with different spatial frameworks, different model conceptualizations. There's a number of different scales that you'll see being represented in the model here as we sort of pass information through the system. There's a number of different physics choices that people can make associated with it, and it's that flexibility and extensibility, which is sort of one key asset, and the other part is that a lot of work has gone into making sure that the code is fairly efficient on high-performance computing systems so that we can do these sort of large domain problems like the continental United States. So looking at the initial model configuration here, we'll get into a lot more detail with this throughout the talk. The basic components that folks have a number of different options in choosing are how the forcing data gets specified. That's bullet number 1. And then we go down to bullet number 2, which is sort of the way that the meteorological information gets exchanged or passed into the land surface. And so there's a number of different column land surface model options that exist within the WRF-Hydro architecture. For the National Water Model, we're using the NOAA MP land surface model, which is in itself is another community land surface model development effort. There's two-way coupling with what we call terrain routing modules. These are going to be subroutines that essentially do routing of overland flow and shallow subsurface flow across the landscape in response to terrain gradients and surface features and things like that. For the National Water Model, there is a step which does essentially a catchment aggregation of certain model states and fluxes, runoff terms essentially, from the model grids for which the land surface model and the terrain routing modules exist on into this NHD plus hydrography. And that hydrography consists of a set of catchments and flow line elements that are mapped across the entire United States and provide a very convenient way and accurate way to collect and organize water in a sort of a very well-structured topology so that we have a clear understanding of what the channel network elements are and where water exists sort of in relation to real water body features. And David Maidment was actually one of the largest advocates for moving to this, recognizing how widely used the NHD plus hydrography is amongst a number of different federal agencies in terms of sharing water information. So to be able to map onto that became a high priority for the National Water Model system. Once we get water mapped into these catchments and into channel networks, then there is a set of channel routing algorithms that exist, and I'll talk briefly as to what's been configured in the National Water Model. This next slide here basically is a full listing of how the different configurations are within the National Water Model. There are 4 different configurations that we use. These configurations are broken out first and foremost as to whether or not we are doing an analysis and assimilation run. That's essentially for hydrological modelers, how we get the model spun up to real time. And then there are a number of different forecast runs. There's 3 different forecast runs that you see listed here. And so whether we're in an analysis configuration or a forecast configuration is those red boxes at the top. So there are 3 forecast configurations, a short range, a medium range, and a long range. The primary difference between those is how long into the future we are making forecasts and with what meteorological data sets are driving those forecasts, and also to a certain degree some of the physics selections that are specified within the WRF-Hydro system that are appropriate for those different time ranges or those different time spans of forecasts. I'm not going to go into this whole diagram because it takes a couple minutes to go through, but I do want people just to be aware that there are these different breakouts of the modeling system that is it's running operationally. I will note that in the analysis and assimilation configuration, this is sort of obviously a key element of the National Water Model because all the forecasts are sort of initialized from this condition, and it presents a continuous analysis of hydrologic conditions for the country. That configuration, it cycles hourly, so it gets updated every hour. It goes back in time for the past 3 hours and pulls in more data from the past 3 hours up until the present, so it's sort of constantly cycling on itself, using as much good quality data as is available over that period of time. and then it in itself is doing some data assimilation. And right now, we are only assimilating USGS real-time available stream gauge information. We are assimilating the flow rate, not the river stage at this point in time, using a fairly simple nudging-based methodology. And the main reasons for taking this fairly simplistic approach to doing this was, for version 1, we really only had a couple of months to set up this data assimilation scheme. We had to develop a whole quality control set of procedures for ranking the data and screening the data. And we actually don't have enough compute resource on the NOAA supercomputers to support some more sophisticated data assimilation methodologies that would be operable over the whole country. So things like an ensemble-based data assimilation framework or variational-based approach. We currently didn't have the compute resources to do that over the whole country. But we're looking into doing those. As Ed mentioned in his talk last week, the whole topic of data assimilation is a high priority of new model development efforts. There's a couple of different efforts going on here, and I know there's a number of different efforts. We're collaborating with folks out in the university community. So that's certainly an active area of research. Just to round out the forecast cycles, I'll just mention the short-range forecast goes out to 15 hours. It uses a very high-resolution numerical weather prediction model as its primary source of forcing data, and it's largely oriented towards flash flood types of forecasting, and those forecasts get updated hourly. The medium-range forecast goes out to 10 days. Right now, it runs once per day, although in the springtime we have an upgrade coming that will cycle 4 times a day. It uses a coarser resolution meteorological model called the Global Forecasting System, and again provides forecasts out to 10 days. The long-range forecast is the one that is quite different. It is an ensemble forecast methodology, whereas the other 2 forecasts are currently only deterministic. This long-range forecast goes out to 30 days. It cycles 4 members 4 times a day, so every day you get 16 different members of forecasts out to 30 days. And it uses a different physics configuration of the model where we don't do the high-resolution terrain routing, and instead we use a mapping of the runoff terms from the column land surface model. So it's a different configuration, it's different forcings, and it has a different calibration than the other configurations. Okay, so that's kind of the very quick description of the different configurations. To take one step back, the WRF-Hydro System itself, as I mentioned, is a fairly flexible and extensible modeling system. There's a number of different configuration options that can be used for a bunch of the different processes that I mentioned: column land surface physics, overland flow, subsurface flow, channel flow. I'm not going to go into this detail on this here, just because we're going to stay focused on the National Water Model configuration. The only other thing I do want to call your attention to on this slide is down at the bottom. For those folks who are interested in doing different kinds of data assimilation research, we do have a version of WRF-Hydro which has been coupled into the DART system, which is the Data Assimilation Research Testbed. And so this uses or has available a number of different filter-based methodologies for hydrologic data assimilation, and is really sort of a open source community toolbox for doing a number of different data assimilation problems, and we're orienting a lot of our new research into looking at options within DART to do that work. Okay, moving on then. We'll get into a lot more detail with each one of these components, but I wanted to show these then updated diagrams as they relate to the different forecast configurations. So this particular diagram shows the configuration of the National Water Model for the analysis and assimilation, the short range and the medium range forecasts. We start with the set of meteorological data, which is produced by a forcing engine, which is basically a set of tools, a set of model scripts, which is processing all of the meteorological inputs into the modeling system, from radar data, from a number of different numerical weather prediction models, and putting that on a common grid for ingest into the model. We'll talk in more detail about what is going on in that forcing engine with respect to some downscaling and bias correction methodologies as well. Once in the model, again, we're running the NOAA land surface model. That's happening on a 1 kilometer grid. Various states and fluxes are two-way coupled with these terrain routing components. The terrain routing components for the National Water Model are happening on a 250-meter grid. So you can see there's a number of different spatial frameworks coming into play here, and there's associated regridding methodologies that are employed to handle the mapping between those two. This is two-way coupling, though, so we are updating states and fluxes between those two components of the model. Then we go into this mapping step where we are mapping runoff terms essentially from the terrain routing module onto the NHD Plus catchment and channel vector network. That then in turn is where water gets put into the river channels, and we do the channel and initial reservoir routing. So again, this is valid for the analysis run, short range, and the medium range forecast run. The next slide here just illustrates the fact that for that long range run, we are not doing that 250-meter terrain routing. Instead, we're mapping directly from the 1 kilometer grid to the NHD Plus catchment network. And so there are some significant differences, as I said, in the physics and the calibration and also in the model behavior that we see out of these different configurations. Okay, so stitching things back together into sort of an engineering type of diagram, we end up with a schematic like this. On this right-hand side, there are what we call the static inputs into the model. This includes things like interpolation weight files, terrain fields, bias correction fields that are static that feed into this forcing engine. On the left-hand side then are all the dynamic inputs, things that are varying with time. So that includes, for the forcing engine, radar data, numerical weather prediction data, data that's available on the INSEP's central computer back on the East Coast. So once those two sets of inputs get combined within the forcing engine, we generate the forcing data for each forecast configuration, and those drive the actual model. So the actual hydro model sits as the lower component here. Into that model, there are also a number of other different static input data sets. Again, this is model configuration files, additional regridding weight files, all of the parameter data for the model gets ingested into the model here. The dynamic input into the model, besides the meteorological forcing data, is the real-time USGS streamflow data for the analysis and the simulation configuration. And then, of course, beyond that is the production of forecasts for each one of those configurations. Okay, a little closer look here at the forcing engine. There are a number of different meteorological variables that are used to drive the National Water Model. It is an energy balance and mass balance continuous hydrologic model for those who organize their hydrologic model conceptualizations in different ways. So to do energy balance methodologies, we need a number of different energy forcing terms coming into the model. This includes temperature, humidity, in our case mixing ratio, surface pressure, wind speed, short and long wave radiation, and of course precipitation. So all of these data sets must be prepared for every forecast configuration. For some of these variables, we do some topographic or terrain downscaling to account for variations over complex terrain in particular. Temperature, humidity, surface pressure, and incoming shortwave radiation are all getting downscaled from their native model grids or model resolutions to the National Water Model grid. At this point in time, we do not have any precipitation downscaling methodologies in operations. We certainly want some. We certainly are working with folks within the Weather Service and within parts of the academic community and exploring a number of different methodologies that can be brought to bear, things like prism-based, regression-based methodologies, particularly for precipitation in the western United States. But there's a number of different opportunities here for folks who are engaged in precipitation downscaling, research, and that is certainly a high priority need for the National Water Model. This forcing engine is all coded up in open source NCL bash scripted environment. It has to meet a certain set of software requirements for the INCEP centralized computing system, which always is a fun set of constraints to work around, but suffice it to say there's nothing proprietary in these codes. We do also utilize the Earth System Modeling Framework regridding tools, which is a fairly generic set of regridding tools, and so those are available within these scripts as well and provide some very fast and efficient ways to transform data between different spatial frameworks. Okay. Where are things standing with this now? Well, we're doing a number of different what we call sort of hydrocentric analyses of the operational precipitation analyses and forecasts, this QPE and QPF of the different model runs. There's a number of different folks between the National Water Center Office of Water Prediction looking at different skill levels of the precipitation forecasts that are coming in as they relate to what's going into the National Water Model, doing verification against other background data sets as well. This leads us to a set of future tasks where we clearly need more effort and work put on expanding the ways in which bias correction are done for those meteorological forecast models and for the radar-driven product as well. I'll go ahead and mention that the radar-driven product is the multi-radar, multi-sensor national radar mosaic analysis, which was developed by the National Severe Storms Lab out of Norman, Oklahoma, and it's kind of one of the frontline operational precipitation analysis products that exist these days. So as we start to do these kinds of analyses, we're starting to overlay where errors or biases in precipitation map to where we have errors and biases in stream flow. So this particular graphic here is actually some work that was done during the first Summer Institute, or the NIFI project, which was done in 2015, that David Mayman helped lead in Tuscaloosa, Alabama. And it looked at areas where we were basically having stream flow prediction skill, as given by the dots, underlined by precipitation biases in this MRMS-driven product, which is the shaded catchments behind. Those are Huck 8s, I believe, of aerial average precipitation mapped on underneath that. And so we're getting to the point now where we can start to look at where the biases in precipitation are intersecting with the biases in stream flow forecasts. And to a large degree, these do tend to map up, but you can certainly see places where the biases do not line up, and this helps guide us in where we need to focus certain efforts, either on improvements in the forcing products or improvements in the model, the hydrologic model formulations. Okay, moving on then, we'll start to get into a bit more details about the physics of the modeling system, of the hydrologic modeling system itself, having just talked about the forcings. So the model setup is like this. Let me go ahead and slide this down so you can see the whole country, since we're not in animation mode here. This, what you see inside the map here on the right-hand side, all of the colored areas are not the bright colors, but anywhere we see sort of the background terrain map is where the National Water Model domain is active. So we call it an NHD+2 encompassing domain. And by that, you can see that now the bright colors, the sort of rainbow colors, which encompass the NHD plus watershed regions, we have basically encompassed all of those areas that are both within the United States and tributary to the United States. And there's some motivations for doing some collaborative work in Canada and Mexico, which is why we're extending out a little bit beyond that. So the model's operating over this whole domain, except for channel routing components. Channel routing components are only active within the colored NHD plus encompassing domain, or those tributary basins. And so there is no channel routing occurring in those other areas in Canada and Mexico. But the 1 kilometer implementation of the NOAA MP land surface model is operating over this entire region. The list of initial data sets which are used to parameterize NOAA MP and the routing terms are listed there below on the left, USGS NLCD land cover data set, which was valid in 2011. That data set is only valid for the CONUS, the continental United States, and so outside of the continental United States, we do default into a different land cover data set. Same thing with the NRCS StatsGo data, which is what's currently used in version 1 of the National Water Model in terms of soil type classifications. We use a monthly evolving climatological vegetation structure as well to parameterize vegetation characteristics, green vegetation fraction, leaf area index, roughness, things like that within the NOAA MP model. Looking at routing processes, the 250-meter routing functions, those are active over the entire shaded terrain part of this domain. So all of the land masses essentially. There is a diffusive wave overland flow. There is a shallow saturated subsurface flow in the vadose zone, which is described in the model, and that is a 2-meter soil column. And then there is this NHD plus catchment aggregation, which is happening, which maps surface and subsurface runoff terms into these NHD plus catchments where we have a base flow parameterization active. And I will provide a little bit more description on that in the following slides. Once we get to channels, for version 1, we are using Muskingum-Kunj methodology, which is a fairly fast and efficient methodology for routing flows on a vector network such as the NHD Plus network. Cedric David and David Maidment and Zongliang Yang at the University of Texas sort of did some early demonstration that doing this over large domains was certainly possible and computationally feasible, and that early work basically made it into, that approach made it into what became the National Water Model. There's a lot of work that needs to be done in sort of rectifying some issues with the NHD Plus network, but that is currently what's in operations. Clearly, there are a lot of other ways in which channel routing can be done via more sophisticated hydraulic routing methodologies, and there is actually quite a bit of work with a number of different groups going on right now to explore which ones of those methods would be appropriate for continental scale deployment, both in terms of computational efficiency, stability, as well as sort of coupling with other parts of the modeling system. The last thing I'll mention here about the channel routing is that there are 1,260 reservoirs that have been defined within version 1 of the National Water Model. Now, it's certainly a small fraction of the total number of reservoirs in the United States, and it does not necessarily include every major reservoir. We did rank prioritization according with reservoir size, but there are a few large reservoirs which were sort of ill-defined in the NHD Plus hydrography in terms of their complexity and in terms of their topology, which made it a little difficult to wrap them into the first version. So as each new version of the National Water Model comes out, you can expect to see more and more reservoirs being included with it, as well as some increases in the sophistication of how reservoirs are represented. And so we'll talk a little bit about that. This slide here then is basically then just the national picture of channel elements in the model, 2.7 million reaches, where the color scale and the thickness of the lines varies as a function of stream order. So from first order streams, which you can't really see on this, all the way up to the Mississippi River, which I believe is a 13th order stream in the NHD. I'd have to double check on that. But you can see that there are a couple of these outside of continental United States tributary basins, some down in Mexico, the upper Columbia River Basin. But there are also some areas that still need to be developed, particularly along the northern tier of the United States, in the Great Plains areas, as well as in the northeastern United States. And that work is currently under development with folks at the National Water Center. Okay, moving on then, getting into a few more details of the physics. This is just a schematic of the NOAA/NOAA MP land surface model. It's like a lot of these land surface models in terms of its representation of energy and water flux exchange with the atmosphere. So the meteorology, of course, for the National Water Model is prescribed, but the National Water Model will simulate processes such as infiltration, water ponding on the surface. It has a multi-layer snowpack, energy-based snowpack formulation, an explicit canopy representation, which has representation of transpiration, canopy evaporation, and bare soil evaporation processes, other things like sublimation from the snowpack. And then in the subsurface, there is vertical soil water transport in NOAA MP through a 4-layer soil column, which extends down to 2 meters at this point in time. That's not a hard and fixed configuration option within WRF-Hydro. We can certainly do a number of different things in terms of the number of different soil layers and the depths of those layers, but because this is a default way that NOAA MP is commonly figured in a number of other modeling systems that are run at NCEP, we had to make a decision to attempt to be somewhat consistent with that. But I would expect to see this constraint relaxed in some future versions so that there's a lot more variability in the structural setup of the subsurface in the land surface model. So once the NOAA MP model executes, as we mentioned earlier, the surface runoff terms and the soil moisture states get disaggregated onto this 250-meter grid, and then the overland flow scheme routes water on the 250-meter grid. The original method of overland flow for WRF-Hydro was adapted from the CAST-2D model, which was developed by Fred Ogden and Pierre Julien back in the mid-90s. We've relaxed that 2D methodology to basically just a steepest descent methodology, basically for computational efficiency at this point in time, sacrificing a little bit of the detail and using a 2D approach. But it does use a diffusive wave methodology, which allows for flow on adverse slopes and ponded water to exist and backwater conditions to exist. It's fairly fast, but you are still bound by current constraints in the shallow water equations when running this scheme. So this does impart some of the more significant computational costs of the modeling system. It does produce estimates of water that is ponded on the surface or inundating the surface up to a point. The main thing to keep in mind here, though, is as we talk about overland flow depths or inundation associated with overland flow, in the first version of the National Water Model, that is only a one-way coupling to what is in the channels. So within the model, we're not doing channel overbank flow back to the landscape, back to the overland flow schemes here. And so there's a significant difference between how inundated waters get characterized, say, from a channel routing methodology using engineering-based approaches to map a hydraulic surface onto a high-resolution landscape versus what this overland flow scheme is doing in the model. It is an issue that is certainly needs to be addressed, and it will be addressed in future versions, but folks who are starting to use and look at different kinds of model output need to be aware of that. Looking at subsurface routing processes then, we use a quasi-steady-state Boussinesq approach. It was adapted from the DHSVM model, which was developed at the University of Washington by Dennis Lettenmeyer and Mark Wigmosta back in the 90s. So within that 2-meter soil column, we basically define a saturated zone from the bottom of the soil column upwards, and where we have saturated flow conditions, or essentially water in excess of field capacity, we allow lateral movement based on the hydraulic gradient in the subsurface. Soil columns on that fine grid can fully saturate and exfiltrate back out to the surface, and that surface exfiltration can participate in overland flow. So we see in the National Water Model, we have started to see evidence of the formation of these shallow saturated layers, particularly in climatologically wet, topographically convergent regions. But even still, we are very careful. This is not a true groundwater model, nor should it be interpreted as such. It is just a representation of where we think soils are saturating and remaining saturated, and that is an important piece of information for looking at future flood risk in terms of how much more water could be taken in by the soil column under different types of meteorological scenarios. Obviously, there's a lot of uncertainty in hydrologic and hydraulic parameters in the subsurface, and so there's really a lot of work that remains to be done in terms of better optimizing specification of these parameters and doing more sophisticated calibration work. Okay, so with that as a basic background of what's going on hydrologically in the model, I'm going to step through a couple of different products that are now sort of in development or operationally being generated by the National Water Modeling System. One of those is a national map, so you'll get an analysis and forecast of soil moisture. In this case, it's cast as percent of saturation for the whole model domain. A lot of the structure you see here is related both to meteorological conditions, sort of the larger scale wet versus dry patterns. This particular graphic here came from May 26th of this year, which was around the time of the Houston flooding, or after the Houston flooding, but the wet period throughout the southern plains and in Texas, all the way up into Kansas there. That was occurring at that time, and you can see those broader scale patterns of soil wetness. You also see finer scale details which are associated with basically the soil type classifications in the model. That's sort of the finer detailed polygonal features that you see here. And then at the largest scales, you see some boundary artifacts where we have different meteorological models driving these analyses. And so at the far northern boundary and then down towards the southern boundary, you can start to see where we change different meteorological data sets, and these different meteorological data sets can have a very significant impact on some of these model states like soil moisture. This product here is developed operationally by the Water Center, and so for all the different configurations of the model, this is available. A product that's under development, which I would imagine will be coming out sometime later this fall or winter, is going to be an operational analysis and forecast of Snowpack. This is an example of this, which we've created here. It's sort of underlying satellite image of the terrain and a 1 kilometer analysis of snow water equivalent over the sort of southern San Juan region, San Luis Valley, Sangre de Cristos of southern Colorado and northern New Mexico. So that's another product that comes out of the land surface model. Estimates of evapotranspiration over the analysis and forecast periods also comes out of the model. Obvious applications for this kind of product are for background estimates of reservoir evaporation, plant water use for agriculture. Obviously, there needs to be some care taken in interpreting this product, but it does provide a nationally consistent analysis and forecast set of products for water loss to the atmosphere. I mentioned earlier that the overland flow scheme does produce what we call a ponded water, sort of dispersed inundation characterization. This is just an example of that during the Houston flood of April of this year. And this is the sort of Galveston Bay region in this little inset map here. And then you can see different areas with greater amounts of water that has accumulated as a result of these heavy rainfall that happened in this area, both under the regions of the heaviest rainfall and then extending up in some of these tributary systems where there was heavy rainfall and runoff was collecting in river bottom areas and in areas where the soils weren't allowing for more rapid infiltration. So this is an interesting forecast guidance product. If you look at it from a regional perspective, I'll sort of move back over here so you can see the national map at that period of time. But it, again, one has to be very careful not to interpret this product as a direct inundation map, such as you'd get out of an engineering type of analysis for channel overbank flow. Okay, another product that comes out of these hydrologic components of the model, again, is this sort of depth to soil saturation. You try and pull this down so you can see a national view. This was also taken from the springtime. This is from a retrospective run. This is May 24th of 2015. You can see that as the darker colors get here, the closer that the diagnosed water table is to the surface. So we see this happening across the southern United States, lower Mississippi River Valley, where it tends to be climatologically wet. Throughout the west, you've got the evidence of melting snowpack and soil saturation associated with that, largely tied to the different mountain ranges. Up in the north, of course, there's some other seasonal melt dynamics happening as well. So again, we're not calling this a groundwater map. It's really just the diagnosed soil saturation levels coming out of the model. but could be put to use for various applications. Okay, to round out the physics descriptions, we have a bucket formulation, which is essentially how we parameterize base flow in the model. Once we map the subsurface runoff terms, or essentially the soil column drainage terms, into these NHD plus catchments, and then these NHD plus catchments use a 2-parameter exponential model to discharge that subsurface runoff back into the NHD plus channel network. So obviously highly conceptualized at this point in time. It's not a real two-way coupling of the subsurface flows with the channel flows at this point in time. And so obviously calibration comes into play in terms of making sure that this base flow parameterization is doing a reasonable job. Channel hydraulics is the next depiction here. Essentially, as I mentioned, we're using in version 1 a Muskingum-Kunge methodology, which runs on the entire NHD plus network. There are obviously some channel parameters that have to be specified with this, and we did not have time to do a very extensive development or estimation of these channel parameters, so what we tend to see are basically just some first order estimates as a function of stream order, which is not a real good way to do this across the whole country, but it was really all we had time to do. And so now there's a lot of work that's going into developing a more robust set of channel parameters, and there's a couple of different groups working on this. But suffice it to say, there's a lot of room for improvement in specifying these channel parameters. We do use a trapezoidal channel, so the key channel parameters here are the bottom width, the side slope, and the roughness that are associated with the channel conditions. Okay, I'm going to step back out then. That's really the guts of the model description. This is an animation which several folks have seen many times before, just sort of demonstrating the sort of flow conditions across the country. This was during a retrospective simulation. I don't have the animation that might run here. No, it's not. Oh, there it goes. So you can start to see a number of different things happening. The sort of very fast moving waves of patterns of runoff or stream flow across the country are associated with the meteorological events. And then lagging behind the passage of a meteorological event is the propagation of the runoff down the channel network following that event, which happens on a much slower time scale. So this goes through the spring of 2015, which again was quite wet down in that southern part of the Great Plains and lower Mississippi River region. But this is all 2.7 million reaches of the NHD Plus network sort of being animated here. And Fernando Salas of the National Water Center, who is a former student of David's, is the person who put this together. So users can now go online and click using the National Water Center's web viewer. Esri also has a viewer for this kind of thing, as well as the HydroShare folks as well, and pull off basically forecasts at any one of those 2.7 million reaches for the country that are represented in the NHD Plus network, and you can get plots kind of like this. These are plots that we've developed here in-house at NCAR, but a lot of these web mapping services have their own plots that have been created where you can basically start to overlay a number of different forecasts with background observations. This upper panel here is for stream flow and the short-range forecast, stream flow for the medium-range forecast, and then essentially accumulated stream flow or accumulated runoff at a point for the long-range ensemble forecast. And that's why you see so many more traces here, so many more model forecast elements, as well as some probability bounds that have been put on these ensemble forecasts. Just want to point out that NHD Plus, as great as it is, does have some artifacts in it. As you start to zoom into different areas of the country, you will see something like this that occurs, where there'll be a very sort of regular feature of changes in channel density that are defined within the NHD Plus system, and that just gets to what underlying data sets were used and digitized into the national NHD Plus network. And I know several of these issues are being worked on by the USGS and its partner agencies, but as you dig into the data, if you start to look at stream flow mapped across the country, you will notice some artifacts like this. Okay, wrapping up the model discussion, model description discussion, there's only a couple more things here. One is the data assimilation system. As I mentioned, right now we're only assimilating real-time USGS stream flow observations. This amounts to about anywhere between 6,000 to 7,500 observations at any point in time. It just depends on what's available. If you go down to the bottom of this graphic, you'll see over time the number of stations that report has increased in total, but there's a very significant seasonal cycle associated with these, which is largely due to ice up of stream flow of river systems, and therefore those gauges go offline seasonally by the USGS. But we have been getting a lot more real-time information flowing into the system. We use this fairly simple nudging-based methodology, and it has its strengths and weaknesses associated with it. It would be a whole other talk to talk about the details of that and what's being developed for next version improvements. But again, as was mentioned by Ed, we're only nudging to observe stream flow conditions at this point in time. We're not updating other background model states, land surface model states at this point in time. And it is allowing those essentially the nudges to taper into a forecast cycle and then to propagate downstream and provide a corrective impact on downstream flows. Looking at reservoirs, as I mentioned, there's 1,260 reservoirs that have been defined by the National Water Center, and those reservoirs are sort of patched into the NHD Plus network, and so we have a representation for connecting those with the NHD Plus channel system in terms of the inflows and the outflows. Right now, it's a very simple passive level pool reservoir scheme. We take the inflows, we uniformly adjust the elevation of the water surface elevation, and then there's 3 different mechanisms for discharge. There is an orifice calculation, a spillway calculation, and then if the reservoir is totally filled up, but yet there's water still coming in, that we can do a direct pass-through. So right now there are no operations data that are feeding into the reservoir model within the National Water Model. That will take a long time to develop because there is no real nationally unified or harmonized reservoir operations database that could be tapped in real time for these kinds of forecasting operations. But that in itself is a long-term development activity that NOAA and the Water Center and a number of different partner agencies are looking to develop. Okay, so summarizing, National Water Model output. Hydrologic outputs are the stream flow, discharge, and velocities at 2.7 million river reaches. At each of the 1,260 reservoirs, there are inflows, outflows, and reservoir elevations, although I would certainly not put too much firm interpretation of the reservoir elevation. And then there are, on the 250-meter grid, this overland flow or ponded water depth that comes out, as well as this depth to soil saturation in the model. On the land surface grids, there are soil moisture states, evapotranspiration, snowpack states, and in some model configurations, some of the energy and water flux terms are being output. And so the Water Center and its partner agencies, as well as the river forecast centers, are now taking this data and creating a number of different forecast products for those. And I think a discussion or presentation on those goes well beyond this talk. Let me wrap up then by just briefly introducing this model evaluation system, and then we can move to some questions. So what we're using to evaluate and then calibrate the National Water Model is this WRF-Hydro tool set. So it's a set of model evaluation tools that was built entirely in R, although there are a couple of tools which have secondary software dependencies. The idea here is that this is an open source community development platform for developing tools for doing stream flow verification, as well as a number of other hydrologic variables, including things like snowpack, soil moisture, evapotranspiration, etc. And basically bring all this under one hood so that you've got a common set of tools which can read model output from WRF-Hydro, National Water Model, or other models, and then do analyses against a number of these other standard data sets which are being generated by both federal and other entities. And so a lot of the tools for the data ingest have already been developed. There are a number of different analysis products which are already available in terms of providing verification metrics. In this particular case, this one here is flow duration sequences, doing water budget partitioning. Some of the other variables I'll just zip right through here are looking at things like evapotranspiration comparisons with other products such as Ameriflux, which is down here in this lower right-hand corner, looking at where the model is high or low biased with respect to, and in ET simulations with respect to Ameriflux, comparisons against other background remotely sensed derivative products. We have the ability to go in sort of station by station and look at validations of ET against a given flux tower site. So by pulling in these data, this is an example of comparing ET fluxes over a number of years at this particular flux tower site in California. So this is model versus observed in that particular case. We do similar things for other variables such as snowpack data, comparing against snowtel observations, comparing against background snow model analyses from SNODAS and other systems as well. Our WRF-Hydro tool has the capability to do some regional aggregation, so we're looking at averaging over either watersheds or large ecoregions and then comparing one set of model analyses to another. This particular graphic here is showing a number of different years of snowpack analysis from the Central Rocky Mountains, indicated in the lower right-hand corner, comparing the National Water Model retrospective runs versus the operational SNODAS analysis, which is a snow data simulation that the Weather Service runs. So combining a bunch of these model analysis and verification tools together, we're now moving into a calibration phase of the National Water Model, and there's a number of different teams working on model calibration in different regions throughout the country, looking at ways to remove a lot of the background model biases that we've seen since the model's been operational in early May of this year. And so we're sort of have keyed into areas where the model isn't performing well and looking at doing a number of different both automated sensitivity and calibration methodologies. This slide here just sort of goes through what the current workflow is that's been developed for this, and there's a sort of a scripted environment that does this by running the model and then doing the automated calibration using the tools that are available in the WRF-Hydro toolkit. This is allowing us to make some fairly significant improvements in removing some of these biases. This is an example from the Suwannee River between Georgia and Florida. The background sort of turquoise color here was the default set of model implementation, which was currently in operations. The black line is the observed conditions, and then after a couple of different calibration iterations was where we got to the orange line here. And so this is just a snapshot. This work is ongoing right now to provide further improvement to that. And so that's one of the main things that's being worked on for the next interim update of the model, which is, again, due out in April. So with that, let me wrap up and say there's really a lot of different opportunities now for folks to engage. As I mentioned earlier, really there's a host of things related to meteorological forcings that can be looked at and making sure analyses of these meteorological products are actually hydrologically relevant. A lot of work is needed and is ongoing in trying to improve the depiction of water management in the model, which is pretty primitive at this point in time. Really developing partnerships to work with folks in different regions to be able to dig into model behavior, calibration, parameter estimation, and process representation is really where we're headed with a lot of this work. That's where the partnerships with the local forecast offices and with local university partners is headed. And really one of the reasons that I think that the Water Center looked at a system like WRF-Hydro as sort of a community-based system where folks could sort of get into it and do this kind of work as well. There's been a lot of discussion on forecast post-processing, so how do we add further value to the raw model forecasts that come out? Any national hydrologic prediction system is going to have uncertainties and biases associated with it, just like any weather model does, and so there's a whole step of sort of post-processing these forecasts to to do bias removal to improve performance, that is certainly possible. I think the work that David and his colleagues are doing related to the application of the hand methodology to come up with inundation mapping is really an excellent example of extending the value of having this national set of operational forecasts and making it more locally relevant. And with that, that's where we sort of get into this paradigm that we're in that the Weather Service calls the research to operations and operations to research cycle. That's this R to O and O to R cycle here. And now that the model's sort of gone into operations, we're down now in this sort of bottom to right-hand side of this curve where we're doing a lot of evaluation and diagnostic analysis of the model, and this is starting to lead to more coordinated research. Some of it's field-oriented research that's being discussed, other of it's more algorithmic development that's being discussed, which will ultimately lead to the next version of upgrades. And this is really where the opportunities for community engagement become a lot more prevalent. So with that, I'll go ahead and stop. I apologize. Just over 2 o'clock here, but I hope that that provides a background with a bit more detail of what's going on under the hood of the National Water Model, and I'm happy to take any questions.
Well, thank you very much, David. And go on.
Oh, go ahead, David.
Oh, thank you very much, David. I really appreciate all the information, and we'll look forward to the discussion.
Yeah, so if we have time and people want to ask a couple questions, I see one now in the chat box that says, how can we obtain the data for channel width, channel side slope, and channel roughness for the 2.7 million river reaches?
Yeah, so that data has been distributed by the National Water Center through their website. It looks like yeah, Fernando Salas is the person who is the contact for that. We are releasing everything because this is an official NOAA model. You know, all the data sets and the code and everything does get officially released through NOAA. I believe they've actually put this data set as a link on their National Water Model webpage. So if you Google National Water Model, read all the way down to the bottom, there are a set of links to things like the forecast image viewer, their dynamic web mapping tools where people can pull up forecasts on a stream network, but also some of the technical descriptions and underlying data sets that are being used within the National Water Model right now. And so basically what you're going to get is a netCDF file of which there are essentially those channel parameters defined for every channel element within the NHD Plus channel network that's used in the National Water Model.
All right, and then there's another question that says, why is the error for stream flow larger in flat areas opposite to the precipitation error? What is the performance of the National Water Model in the extreme weather or in steep mountain areas?
Yeah, that's a couple of good questions there. Let me zip back up. So our flat areas are mostly, I think you're referring to the Great Plains and the southeastern seaboard, sort of the coastal plains of the southeast. There are different challenges in each one of those areas. Taking the Great Plains, that's been a problem area for many hydrologic models, although not all. And we've been doing a set of diagnostics there, and there's a couple of things that have really popped up. One is the nature of the surface water-groundwater coupling and the fact that you have a lot of disparate gaining and losing reaches across that area, which are sort of problematic to define in a national model as water flows across those networks. There's also the discontinuity of the channel network in those areas. The NHD Plus system really forces runoff to be collected and moved into a continuous channel network. And in those areas that are very flat, they don't always contribute the way that it might appear that they do. And so you get the appearance, or you get the formation of things like playas and channel systems which basically just don't drain into a continuous network, although in the NHD Plus network, they do basically they're fully tributary. And so we've seen that this combination of fairly, insufficient treatment of groundwater coupling, along with this concept of a bit more complicated hydrologic connectivity, is one of the main reasons that we're suffering in those areas in the Great Plains. On the eastern coastal plain, it's largely a soil hydrology issue that's related to some problems in how the sandy soils, particularly in the southeastern United States, were being parameterized and solved in the NOAA MP scheme, as well as some shortcomings in groundwater coupling in those areas, and that, at least according to the water balance studies that we've seen, we're not seeing that basically all of the rain, and combined, if you do a full water budget with evapotranspiration, all comes out as runoff, and that there's actually a fairly significant amount of freshwater discharge to the oceans in Florida and in some of those areas in the southeastern United States via subsurface flow. And the National Water Model is just not representing that kind of process yet. So those are some of the leading things that we've been looking at and diagnosing, basically with the suite of tools, and looking at not just at stream flow, but at multiple hydrologic variables and trying to pin down that. In steeper mountain areas, we actually do tend to do a lot better, but we do have higher precipitation and forcing data uncertainty in those areas, and so those are places where you can also see the pattern of precip bias and hydrologic model bias get a little out of whack. But we found that in steep mountain areas, when we get the forcing right, the hydrologic model and the Snowpack model, particularly in the latest version that we'll be releasing in April, are actually doing a fairly faithful job. So there's one from Patrick. Okay, so what priority has been given to adding nutrient tracking or sediment flow? That is an excellent question. There is a future goal, coordinated activity that the National Water Center is looking at developing and elaborating on, which is focused on water quality, modeling and prediction. That is, I forget exactly what year it is, I think 2018 or 2019. And so in that time frame, there is a much larger coordinated effort that's being planned. For right now, there isn't anything immediately available or being done to model, particularly in a reactive sense, nutrients or water chemistry or sediment. There are some groups who are now putting in tracer methodologies into the National Water Model. Say you get a mine spill or something like that, or some kind of chemical spill, at least you can trace in a passive sense flow down the channel network. And so that'll be some of the first capabilities that I think we see, largely done as post-processes to the model. But the future goal, as outlined by the Water Center, is certainly to have a much more sophisticated water quality capability in the model. Other questions? Let's see. Moving fast. Emily,
yeah, wow, we got a lot coming in here.
Go ahead and pick.
Let's see. So there's one question that says, how long of a time period did the National Water Model use to spin up when it was first implemented?
That's a great question. The answer to that is very regionally dependent in terms of when you reach equilibrium. What we do as a minimum is 5 years. So if we do a version upgrade and then we're going to do a new set of work, we will do a 5-year spin-up of the model. That tends to be on the safe side for most areas of the country, but for particularly the dry desert southwest regions of the country, there are times and places where that may not even be adequate because of some of the slower processes. But given that we don't have a very deep subsurface and that across the continental United States we don't have very deep persistent snowpack conditions like what exist up in Canada, 5 years does tend to be adequate. So that's the rule of thumb that we're using right now. We've done small basin, more extreme tests of this, where we basically go in and initialize the model with end members fully dry or fully saturated conditions, along with sort of a best guess middle-of-the-road analysis, and you see when those solutions emerge, when those solutions converge. In different configurations of WRF-Hydro, you get different answers, but what we've seen in the configurations that's similar to the National Water Model, that can take up to about 7 years. But that's, again, not taking into account deeper groundwater processes. So I don't want to say 7 years is good for all models. It's just for the model configuration that we have and some of the range of conditions that we're looking at, 5-ish years is what we've been using. Can you find the list of reservoirs that are included in NHD Plus version 2? The reservoirs in NHD Plus version 2 are just part of NHD Plus version 2. The reservoirs that are in the National Water Model are a subset, and that is a question for the National Water Center in terms of exactly what water bodies and things like that in the format of the data set that will be released and when. So yeah, I would defer that question to the National Water Center. Fernando, okay, he's providing instructions. Let's see, Jaikui, how long time period? Okay, that was a spin up. Yiling, is there an iteration between surface water, groundwater interaction for a converged solution? Another good question. In version 1, there isn't. They basically they run interactively each hour, but within the hour they're not interactive with each other. So that's the main difference there, is that each component will run for a full hour before everything gets sort of coupled back and synced up. And that's the same thing is true with the coupling to the column land surface model. We're now looking at experimenting with doing that coupling on a much finer time step so that the fields are essentially more tightly coupled by more frequent calls. Sanjeev, similarities and differences among WRF-Hydro, NOAA and National Water Model. Well, so I guess the way to put this is that NOAA is a component of WRF-Hydro, and that the National Water Model is one configuration of the WRF-Hydro system. So it's not that they're similar or different. They are different parts of each other depending on what gets configured. So NOAA is just one component of WRF-Hydro and therefore one component of the National Water Model. The National Water Model is just one instance of the WRF-Hydro system. So I hope that makes sense. Let's see. I think that's about it for questions that I can see, Emily.
Yeah, I think you got them all. Thanks, Dave. So we did run a little bit over, so I think we should go ahead and let everyone go. But again, thank you so much for being here this afternoon, Dave. Let's see. I want to remind everyone that we will have a presentation next week from Peyron Lin and Adnan Rajiv and some of the other student course coordinators that were at the Summer Institute last year. So we'll hear from the students regarding some of the projects that they put together during their time at the Summer Institute at the National Water Center. So Dave, I guess we did record this presentation, and so we'll go ahead and post it to the Quasi website if that's okay.
That is totally fine. I also noticed there was a question somebody wanted the presentation. I will go ahead and crank that into a PDF and send it to you, Emily.
Awesome. And can we post that as well, or do you want me to hang on to that?
Nope, absolutely.
Okay, great. Thanks so much. All right, everyone. Well, we will talk to you next Thursday at 3 o'clock for the next presentation in this webinar series.
Thanks.
All right, thank you.